Video we'll talk briefly about constrained optimization using Lagrange multipliers. So we won't carry out much of the mathematics by hand. We'll cheat a little bit and use some algebraic computer algebra systems to solve for us, including Wolfram Alpha. And so first of all, we've got to think about what kinds of problems this method will allow us to solve. Well, first of all, our objective is to minimize or maximize some objective function, which we'll call f of xy. So in this case, the output depends on two input variables, x and y, and we have some constraint placed upon this objective function. We'll say g of xy equals 0. Now, we'll talk about how this happens because our constraints are often not set up such that we want some function of x plus some function of y to equal 0 or any sort of method like that, but we can pull a little trick to make that happen. So the method of Lagrange multipliers is stated as follows. To optimize an objective function f of xy subject to the constraint g of xy equals 0, do the following. Define or form a new function called capital F of x, comma y, comma lambda, Greek letter, equals little f of xy, the objective function, plus lambda times g of xy. Now, lambda is called the Lagrange multiplier, and it turns out that we won't discuss the mathematical derivation of this because it's quite complicated. But lambda is essentially a multiplier that, quote unquote, makes it all work out. So the procedure goes as follows. Set the partial derivatives of f equal to 0. So find the derivative with respect to x, derivative with respect to y, and the derivative with respect to lambda of the capital F function that we created out of our objective function and our constraint. And solve these to find the critical points. The solution to the constrained optimization problem, if it exists, will occur at one of these critical points. Well, that doesn't sound too promising, but let's check it out. So in this example, we have a Cobb-Douglas model for Ford Motor Company. It's given by P of L comma C equals this messy thing. And the output is in thousands of vehicles. L is the labor cost and C is the capital expenditure, both in millions of dollars. We have some information about Ford Motor Company, and assuming that Ford has $34,131 million or $34,131 million to spend on labor and capital in 2000, how much should it have spent on labor and how much should it have spent on capital expenditures in order to maximize vehicle production? So our problem setup is we want to maximize the production function, and we're going to relabel everything in terms of f, x, and y because using tools like Wolfram Alpha can get sometimes a little sticky if we try to use other letters, because sometimes it tries to mistake those as units or constants, and we don't want to do that. Furthermore, we're subject to the constraint that x plus y has to equal $34,131 million. That is, the number of millions of dollars spent on labor plus the number of millions of dollars spent on capital should sum to this amount. Now, of course, if this is our budget, then we may want an inequality less than or equal to, but this method does not apply to inequalities. And so it's not quite as robust as we'd like it to be, but all right, well, let's see what we can do with $34 billion. So g of x comma y is the constraint with 0 on the right. Now our constraint seems to be g of xy equals 34,131. But if we do a simple little bit of rearranging, if we take the 34,131 and we subtract it over to the left, then we will have precisely 0 on the right, i.e. x plus y minus 34,131 equals 0. And that by definition is what g of xy is, this x plus y minus 34,131 quantity. The next thing we need to do is define this new function, which is going to equal f of xy, our original function, there it is, f of xy plus lambda times the g of xy, which is the x plus y minus 34,131. Next, we want to set the partial derivatives of f equal to 0, i.e. f sub x equals 0, f sub y equals 0, f sub lambda equals 0. So let's go over Wolfram Alpha and do a little bit of work. So I've simply entered in derivative of that capital F of xy function. Now I've used x, y, and z for lambda. I encountered some difficulties trying to use L or trying to use other symbols. I've just gone with z just to make things simpler. So z is my Lagrange multiplier. That's my lambda. X is labor cost. Y is capital expenditures. And so then it outputs the three partial derivatives. Capital F sub x, capital F sub y, and capital F sub z. So I'm going to write those down, and I'm told that I should take capital F sub x and set it equal to 0, So it's not that it is equal to 0, it's that I'm setting it equal to 0. And same thing with capital F sub y, and same thing with capital F sub z. All right, well now, oh, and by the way, just a reminder, lambda is just a multiplier that allows to solve the constraint problem. It serves as a gateway quantity for finding the critical point x comma y. All right, so don't worry too much about that. Using Wolfram Alpha, we now go about solving this system, okay? So what we're going to do is we're going to type in solve, and we're going to say f, our capital F sub x function, there it is, set it equal to 0. Easy way to grab that function is to look at the partial derivative and click on plain text, and then where it says Wolfram language plain text output, simply copy and paste that over here, do equal 0, put a comma, and then go with the next function, f sub y, and oops, that's f sub z, capital F sub y, and I'll take that right there, I'll copy it, and then I'll paste it, there it is, right there, and I'm gonna, oops, that's actually this one, right here, and I'm gonna set that equal to 0, and same thing, I'm gonna copy and paste the output for f, capital F sub z, which is negative 34, 131 plus x plus y, and I'm going to set that equal to 0 as well, and nope, I think I did it in a different order here, but nonetheless, this is precisely what we want, and then the result appears. It says x, and you've got to kind of weed through this a little bit. X is equal to that, which is approximately 15,612.5. Y is that, which is approximately 18,518.5. And z, which you'll see often strange things, it'll be a negative 0.275663. Doesn't really mean anything. We don't really do anything with the lambda. Again, it's just sort of there as a mathematical placeholder. So there's our output. That's what we get from Wolfram Alpha. It's solved, it does all the work for us. And now we have a critical point. This tells us that at the point 15,612.5, 18,518.5, we have a critical point. That means that this is a candidate right now for being a maximum or minimum. So how do we know whether this is a minimum, and how do we know this is a minimum and not a maximum? That is, if I tell my boss, spend this much on labor and millions of dollars, spend this much on capital expenditures and millions of dollars, and if I'm wrong, I'm in a little bit of trouble. So we can test the outputs of surrounding points, but it's going to be cumbersome since the points chosen must satisfy the constraints, and the constraint in this case. Well, I just generated a table. I just kind of picked some x values that are below and above 15,612.5. I'm not saying this is the optimal route, but I went about 400 under and about 400 over, and I just went in increments of 100, as you can see. And then my y column is just this minus, or sorry, 34,131 minus this, because these two have to add up to 34,131. And then I tested them in our original objective function, and I found that, well, you know what? If I go back here, or if I figure out what the output is at this point, at each of these points, that's the total production I get. And the highest I see here is 9,380.503. Now that's 9,380,503 vehicles that could be produced under those conditions. Well, that's pretty close to our constraint. But if I plug in our critical point, if I plug in the critical point, I will find that I can do a little bit better. It actually turns out to be 9,381.5 or something like that, or 9,808.5. So anyway, in any case, this is just slightly higher, which convinces me that at least if I pick neighboring points, I actually get lower production outputs rather than higher ones. If I saw higher numbers here than the production output at this critical point, then I would know that I haven't found a minimum, and a maximum, and therefore I would proceed with caution to say that that's not necessarily a maximum. Okay, so our conclusion is that spending $15.615 billion on labor and 5,185 should read billion on capital will result in a maximal production of about 9.381 million vehicles. Done deal. That's it. And that's the method that we would mathematically use in order to compute the critical point. Now, it turns out, and you've got to be really careful here, if you want to maximize this, we can say maximize f of x comma y equals, and take away this constraint, this plus lambda stuff. And a couple of things could happen. First of all, it tells me that, subject to x plus y equals 34,131. And in this case, things work out fine. We actually do get 9,380.51 at that point right there. But keep in mind that this is finding global maxima, meaning the if this is the multivariable function, and this blue line represents the slice created by the constraint x plus y equals 34,131, then I am just hoping that there isn't more than one maximum in that region, or I'm also assuming that there exists a global maximum. And in this case, it doesn't seem to matter. It's able to give me that output as well. But keep in mind that this method is not flawless, and neither is doing it the long way as proposed in this document, but it certainly does ensure that the critical points we're finding is mathematically sound. And we are assuming that Wolfram Alpha is doing mathematically sound work and it understands what we want. It seemed to do at that time, but just be careful